As we have seen in previous videos, what is displacement thickness, momentum thickness as well as energy thickness from conservation of mass, conservation of energy and conservation of momentum. So let us apply all these equations, that is conservation of mass, energy as well as momentum, along with Newton's second law of motions in boundary layer theory. So let us study what is von Karman's momentum integral equation. To study von Karman's momentum integral equation, first thing we observe over here in the topic itself is the word momentum. So over here we have to apply law of conservation of momentum. As well as integral equation, where we have to consider your boundary layer, which can be integrated from y is equals to 0 to the topmost layer of the boundary layer, that will be delta. So for here we have to consider, a plate which will be having this point. This point is called as the leading edge. From the leading edge, if there is a fluid which is flowing with velocity u, then it will form a boundary layer which will be in this direction. As the distance x increases from the leading edge, the thickness of the boundary layer increases. So now let us take a section over here between the boundary layer. From the leading edge, let us take this distance as x and this thickness as equals to dx. Let us name these all points over here. So let us name this as A, B, C as well as D. So let us take this entire part and zoom it, and I'll draw this separately so we will get a picture over here. So since this will be point A, this will be point B, this will be point C, this will be point D. Now since we have got the broader picture of this boundary layer, the thickness of the boundary layer along horizontal direction is dx. Now let us consider the velocity gradient along this entire part. So the velocity gradient will look something like this, and at a distance of y from the solid surface, we will take this small value dy, that is small thickness dy in this boundary layer. So now here this will be the velocity gradient, but as we see, as the velocity is increasing from y is equals to 0 to y is equals to delta, where thickness of this entire strip is given as dy. Now over here we can already see over here there is velocity gradient. At y is equals to 0, u will be equals to 0, and at y is equals to delta or beyond that, u will be equals to u infinity, or it is also called as the free stream velocity. Now at y is equals to some value over here, let us consider the velocity as small u, which is greater than 0. This small u is greater than 0, but it is less than the free stream velocity. And over here also this corresponds to these values, that is it lies between 0 to delta, that are the velocities. So here we know that velocity, that is u, is a function of y. So that we have considered over here. Now let us apply mass flow rate or conservation of mass for this entire part. So let us apply conservation of mass. So for conservation of mass, let us draw this diagram again. So there will be 4 points over here. This point is A, B, C, D. This is the boundary layer and it is having a thickness of dx. So at a distance y from this point, at a distance y, we have taken a elemental strip. Okay, so this elemental strip has a very small thickness along y direction, but along z direction it will have some amount of thickness, that will be b. So in short, this strip will look something like this, having a vertical direction, having a vertical length as dy and along this direction as b. So we have to calculate the mass flow rate through this entire part. So we all know that the mass flow rate, we have to calculate the mass flow rate. So the mass flow rate will be given as m dot a, m dot 1 or m dot a, whatever prefix may use, will be equals to rho into area of cross section into velocity. Now since we have considered the velocity at distance y as equals to u, here the velocity will be u, and the area of cross section will be given as this entire area, that will be equals to dy into b. So this will be equals to m dot 1 will be equals to rho into b into dy into u. Now since this is only valid for this small strip, but we don't want this for mass flow rate for this entire strip, we need that for that entire surface. Hence we have to integrate from its lower limit, which is y is equals to 0, till its upper limit where the value is delta, that is the length of the boundary layer. So let us integrate between the limits 0 to delta, that is the mass flow rate between this entire part, or we can say the mass flow rate between A to B, that is AB. Similarly, we can calculate the mass flow rate through this entire part, that is through DC. Now that mass flow rate can be calculated as, this is mass flow rate which is coming inside, and this will be the mass flow rate which will be leaving. So the mass flow rate which is leaving can be written as m dot out, can be written as m dot in x plus dx. So that x plus ds. So let us calculate what is m dot out. So m dot out is equals to m dot in x plus dx. So just for our convenience, let us write this as m dot 2 is equals to m dot 1 x plus dx. Now we have to expand this equation with the help of Taylor series. Now we know that for a Taylor series, f of x plus h is equals to f of x plus f dash of x upon 1 factorial into dx plus f double dash of x upon 2 factorial into dx square, so on and so forth. So this relation we have to expand by Taylor series. So we can use this Taylor series to expand this entire part, that is the right hand side. So here also this is m1 dot x plus dx. So this will give us, that is m dot x plus m dot 1 x dash upon 1 factorial into dx plus m dot 1 double dash of upon 2 factorial into dx plus higher order terms. Now while expanding this part, we consider the thickness of this entire dx is almost equals to 0. It is a very short amount of strip. So the higher values of dx raised to n will tend to 0 when n will be greater than 2. So from 2 onwards to the till infinity, all the values of this will be equals to 0 because it is negligible in comparison. So now what we have to focus on is this entire part. So now let us understand this part. The mass flow rate is not only a function of x, it is a function of y as well as function of z. Since it is a function of three quantities along with it is a function of time. So with all this mass flow rate being function of all these four physical quantities, we cannot write m.1x as a complete derivative. We have to replace that by a partial derivative. So let us write down this part as equals to m.1x plus a dx is equals to m.1x plus dou by dou x of m.1x without m, this is the dot not the dash, into dx upon 1 factorial will be 1. Now let us substitute what is the value of m dot x. Now what is actually m dot x is, from the previous equation, m dot x is actually the mass flow rate at a distance of x from the leading edge. So now the mass flow rate at a distance from a leading edge is actually the mass flow rate which is coming inside, that is m dot in. So m dot in or m dot 1 is one and the same thing. So let us substitute in that equation. So we have to substitute, that is m dot 1x as this value. So let us substitute in this equation. So what do we get over here is integral 0 to delta rho into b into y into u plus dou by dou x into integral 0 to delta into rho into b into dy u into dx. So this is the entire part which we have got. So now we have seen what is the mass flow rate which is coming inside. We have seen what is the mass flow rate which is leaving. So now if we draw the diagram all over again, we can notice one thing over here. A, B, C, D. So mass flow in is this part, m dot in, thus, and mass flow out is m dot out over here, but there is something remaining over here which is this entire part. So we have to take into consideration what is the mass flow rate through AD. So we can replace this m dot in by, we had already seen m dot by x, or m dot mass flow rate through AB, which is holds true for this condition. Similarly, we can replace m dot out, we have seen this is m dot 1x plus dx in the previous part, by m dot, that is mass flow rate through DC. So m dot through DC. Now what we need is the mass flow rate which is flowing through this entire part. So obviously we know what is the mass flow rate which is leaving, we know which is the mass flow rate which is coming inside. The difference between them will give us the mass flow rate through AD. So from the law of conservation of mass, we can write over here m dot BC, which is the larger mass flow rate, minus m dot AB, m dot rather DC, not BC, minus m dot AB will be equals to m dot AD. So mass flow rate out minus mass flow rate in is equals to the mass flow rate which is going through AD. So let us substitute those values. M dot out, which we have already seen, that is equals to, therefore this is integral 0 to delta rho B dy into U plus dou by dou x into integral 0 to delta rho B dy U into dx. So this is just mass flow rate which is through DC. Now what is mass flow rate through AB, which will substitute over here? So it is integral of 0 to delta into rho into B into dy into small u. That is m dot in, that will be equals to m dot ad. Now obviously we can see the first term of this entire part is same, so these two have been cancelled. So now what we are going to get over here, that is m dot ad, that is mass flow rate through AD, is dou by dou x integral 0 to delta rho into B into dy into U into dx. So this is the mass flow rate through AD. So now what we have applied over here is conservation of mass. Now since we have got the mass over here, we can apply what is conservation of energy in this equation. So to apply conservation of momentum in this equation, not energy. So now to apply conservation of momentum, we know that momentum is product of mass into velocity. So let us multiply all these mass flow rates by the individual velocities at that position. So then only we'll get what is momentum in which is coming inside and the momentum which is leaving. So now let us apply this. So applying law of conservation of momentum. So let us draw the diagram again. So there were 4 dots over here. So this is how the section looks like. So this is A, B, C, D. This part is a dx. And here we have a small amount of velocity gradient, and at a distance y, we have a strip that is a dy. So now we have to apply momentum in this entire part. So now we have mass flow rate through AB, we have mass flow rate through DC, and we have mass flow rate through AD. So now let us apply conservation of momentum for this entire part. So first we'll use momentum through AB. So that will be equals to m dot AB into the velocity u. So the velocity u over here will be changing from y is equals to 0 to y is equals to delta. So this can be written as equals to integral 0 to delta, which we have seen earlier, that is a rho b dy into u, which is also multiplied again by u, and u is a function of y, so we can integrate this from 0 to delta. So this is the momentum through AB. Let us calculate what is momentum through DC as well as the momentum through AD. So momentum through DC. That will be equals to integral 0 to delta rho b dy u into here also the velocity with which it will be leaving is under this boundary layer, that is also a function of y. Hence here the velocity which we'll be using, that will be again y. So this will be plus dou by dou x into integral 0 to delta rho into b into dy into u into dx. So this was the mass. So now this mass has to be multiplied by the velocity. Now u is under the boundary layer, hence we can have to multiply by a suffix u. So over here we'll get this entire part as integral 0 to delta rho into b into dy into u square plus dou by dou x into integral 0 to delta rho into b into dy into u square into dx. So this is the value of momentum through dc. So we have multiplied mass by its velocity. Now let us see for the last part, which is quite important over here, that is the momentum through AD. Now since it is the topmost part of this entire thing, so the velocity over here will be u infinity, or we can take that as u over here. So now let us write down the momentum over here. So the momentum through momentum through AD will be equals to, rather we'll write it over here, mass flow rate through AD into capital U, and this was mass flow rate through DC into small u. Why u small u? Because it is under the boundary layer. Why it is capital U? Because it is beyond the boundary layer. So now let us apply the formula, that is, this is dou by dou x integral 0 to delta, that is rho u b into dy into dx into capital U. Now capital U is not a function of y, because it is at the periphery of the boundary layer, where the boundary layer ends, and actually the velocity will be the 99% of the free stream velocity. So we can keep as it is in this equation. Now why we are applying this momentum equation over here, let us understand this part. So we have our solid surface, we have this as our leading edge, and we have the velocity which is flowing in the positive direction of x-axis. So during this part there is a small amount of boundary layer generation. Now during this boundary layer generation, what happens is we have taken this small layer of this boundary layer. So now the velocity which is moving, or the force due to its velocity, it is dragging this in this direction. We can put this force as the driving force. So due to this there will be some velocity gradient. Now this driving force is parallel to the solid surface, but the shear force is applied in the opposite direction. So over here this is the shear force which is in the opposite direction. This shear force consists of the adhesive force between the fluid and the solid, as well as the viscosity, the force due to the viscosity of the fluid. So the driving force is taking the fluid away from that part, whereas the restoring or the shear force is against this surface. So now if I had to calculate the shear force for a small strip y at a distance of y, that can be written as, or we can take for this bottom surface as, equals to tau 0 is the shear stress, rather not the shear force, shear stress into area. Now the shear stress will be multiplied by b into dx, because this displacement over here is dx, and the shear force is always applied parallel to the area of cross section. So over here if we have to draw the diagram of shear force, so this would have been something like this, where the shear force is applied on the topmost surface, that is Ft, or let us consider Ft as, or Fs as the shear force which is tangential to this entire part, where this displacement is a dx and this displacement is equals to b. So the shear stress into BDX will give us the shear force. Obviously it will be negative, it will be in the opposite direction, because it is in the opposite direction. The driving force is towards right, whereas the restoring force or the shear force on the liquid will be towards the left. That will be equals to the rate of change of momentum. So we have established now what is the relation between the previous section, or the our motive to calculate the momentum thickness, or applying law of conservation of momentum. So now we have established this part. Now rate of change of momentum, let us clear out this part on the left hand side. So over here let us write down, that is minus tau into b into dx is rate of change of momentum, that is d by dt of final momentum minus initial momentum. Now over here we know that d by dt of this is mass into v2 minus mass into v1, provided the mass is obviously it is a control volume, the mass of that entire part does not change. But if we take this mass outside, so we can get this as d by dt of m into v2 minus v1. Now this is what we are interested in. In the previous section we had not taken mass into velocity, we had taken the mass flow rate and into the difference of its velocity. So now we are relatable to the things which we have done previously. So let us relate this shear force with conservation of momentum. So for that we'll draw the diagram all over again. So now over here we have this 4 points A, B, C as well as D. So in this, the drag force or the shear force is towards left, so this is shear stress is towards left, and we have to calculate what is the change in momentum. So the change in momentum or the force, we can write force is equals to mass into acceleration, or mass into v2 minus m dot into v2 minus v1. So now this can be written as minus of tau into b into dx, which is the left hand side. Over here the final momentum, which is momentum of DC minus the initial momentum, that is momentum of AB, minus the momentum which is over here through AD. So let us write down this. So the momentum through DC, that is the final momentum, minus initial momentum through AB minus momentum through AD. So this is how we have, that is final minus initial. Initial has two parts, that is AB as well as DC. So now we can use this, or we have already calculated this part. So let us write down this minus tau into B into dx, that is the left hand side, which is equals to the momentum through DC. So let us go in the previous part and let us check out what momentum through DC which we have calculated. So the momentum through DC is this entire value. So let us substitute that. So this is rho integral 0 to delta rho b dy into u square plus dou by dou x into integral 0 to delta rho b dy into u square into dx. So this is just the value of momentum through dc, pardon my spelling for momentum, and then momentum through AB, that can be written as minus of integral 0 to delta rho b dy into, this part will remain constant, that will be the u square, minus the momentum through AD. So that also we have calculated momentum through AD as equals to rho ub into dy dx into u along with dou by dou x. So this is minus of dou by dou x integral of 0 to delta rho into b into dy into small u into capital U into dx. So this part we have got. Over here we have got this two parts as same, so that can be cancelled, and we have to deal with these two terms. So while dealing with these two terms, we can take out few things which are common, that is rho b into dy over here, that is rho b dy, as well as dx in both the parts, dou by dou x and dou by dou x in both the parts. Integral value is also constant, which separates out only two different terms over here, u square and small u into capital U. Small u is the velocity when it is a function of time, capital U is the free stream velocity. So let us apply this and write it down. So this will be equals to minus of tau into b into dx integral 0 to delta dou by dou x, along with that, very important, rho into b into dy into dx also, and inside the bracket small u square minus small u into capital U. So these are the all terms which are covered. Now let us convert this into the things which we know, that is momentum thickness, displacement thickness and energy thickness. So all these values, that is rho b into dx, all are constant, but here we have to convert this part into momentum thickness. Now there is a small thing which we have missed over here, that is a b dx and b dx, both of the things will go away, and this will be minus tau is equals to dou by dou x into integral 0 to delta rho into, let us take over here small u common, along with small u we can divide this by capital U or u infinity. So this will be equals to 1, this will be equals to u. So this can be written as minus of tau into, tau is equals to dou by dou x into integral 0 to delta rho into dy. Now let us take capital U square common from this entire term. So if we take u infinity or capital U square common, what do we get over here? That is small u square upon capital U square minus of u upon capital U. So this is the term which we get. So now let us write down this further. Let us take this minus sign over here. So this is minus tau is equals to dou by dou x into integral 0 to delta into rho into capital U square into this part over here. We can take small u upon capital U as common. Minus sign will go inside, so this part will switch. So this will be 1 minus small u upon capital U or u upon u infinity into dy. So this rho into u square, that is the free stream velocity, is constant, so that is come outside the sign, outside the derivative, so that is minus tau is equals to rho into capital U square dou by dou x integral 0 to delta into small u upon capital U into 1 minus small u upon capital U into dy. Now this part is nothing but, we know this part is nothing but, that is momentum thickness. So we can write this as tau is equals to rho into u square dou by dou x of theta. So this is what is one Karman's this is what is one Karman's momentum integral equation, which is in terms of shear stress, that is equals to rho into u square into dou by dou x of theta. Now this shear stress, which we have represented in tau 0 or shear stress, this can be also represented in terms of shear force. Now the shear force can be written as over here, that is tau is equals to shear force upon b into dx. So the shear force will be tau b dx. So this will be equals to rho u square into dou by dou x of theta, that is value of shear stress, into b into dx. So this is value of shear force. So we have got what is shear force and we have got what is von Karman's momentum integral equation. So I hope you have understood how we apply the law of conservation of momentum and linking the law of conservation of momentum to the Newton's second law of motion. So together we have calculated what is von Karman's momentum equation. Thank you.